Okay, we got everything up here. I have posted a quiz for the day. It's actually two quizzes. I did that this morning. We're not going to take a look at that first off because I want to finish some things up in chapter 4 before we actually get into it. But if you want to get it downloaded, and those of you that I critiqued, if you want to take another shot at a different phone app, because my wife pointed out to me that there's lots of phone apps out there that can take pictures and probably do a better job than some of you guys did earlier. So there's only a couple of you that had issues, but I think it'd be well worth it to make it easier for me to see what you've done. So on with this part of the show. So where we left off with was interference and pre-emphasis. And the interference is going to be the first thing I'm going to talk about, and then that will lead naturally into pre-emphasis when I go ahead and take a look at some aspects of interference, and then that will reflect upon noise, and then that will reflect upon pre-emphasis. And then that will also lead into this discussion a little bit later on when we talk about how FM stereo is produced in FM broadcasting. And then further to add to that, I've got a software-defined radio, the RTL SDR, hooked up today. And those of you in the lab are starting to work with that radio. If you had your own radio, you'd be able to do exactly what I'm going to demo, but I know that Daniel is sending you captures as well. So, interference and pre-emphasis. So we have interference, that's a fact of life in communications, and we also have noise present. Both of those topics are more along the lines of what we would do with random signal modeling, and that doesn't really come up in this book until chapter 7, and that's a chapter that's covered completely in Comm Systems 2, which reminds me, now that I'm mentioning that, Professor Semiari is going to be teaching Comm Systems 2 for me in the fall, and I'm really worried that we're not going to have enough students. So I'm just wanting to get you thinking, if you're at all thinking of taking it, if you wouldn't mind letting me know in Slack or something, because the dean is going to be very brutal with canceling classes that don't have enough people. It was going to be brutal before COVID-19, but now that COVID-19 is here, it's even more brutal because of budget cutting and budget issues that we're concerned about as a campus. Our report today is our enrollment is looking good, and our graduate enrollment is looking good too. They're really happy with that. But there's so many factors that enter in to all of this that we just can't say what's going to happen. So the interference that we're going to start off with is interference in angle modulation in the form of a sinusoidal tone, and we've certainly done that before. So we're going to assume that we have an interfering tone, and it's sitting at omega I, which could be Fi in hertz, above the carrier at Fc. So we go back to our complex envelope that we've used in the past when we were studying interference in amplitude modulation, and we form that complex envelope by expanding everything in terms of the carrier at omega c. So we write this expansion in terms of omega c, and then what we're doing is our unmodulated carrier will come along here, and it hits the e to the j omega c, so it creates an unmodulated carrier. And then we've got the interference tone expanded out in the complex envelope notation to be AI cosine omega it plus j omega I sine omega it. So that is just, in reality, just AI e to the j omega it. And then, of course, when you plug that inside there and then take the real part, you'll get back, mathematically speaking, it just comes back to that form. But we wanted to get it in terms of a complex envelope so that you can see what's what. So we can see that in our complex envelope, which is what is sitting in here, inside the square brackets, that's got a constant term, which represents our unmodulated carrier, and then our jammer or interfering term that has real and imaginary parts. And then we go back to what we did back in chapter 3 when we were looking at amplitude modulation. We particularly focused on getting the envelope of the complex envelope. But now that we're doing angle modulation, we're not so much interested in that. As a matter of fact, I shouldn't say we don't care about it. What it comes down to, though, is when we were talking about the use of a limiter or clipping circuit in a front end of an FM or angle modulated receiver, that's to remove the envelope fluctuation. So if the envelope fluctuations are mild, we can get rid of those with our limiter. But what we're interested in for phase or angle modulation in general is the envelope phase. So that's just the angle associated with this R tilde, and that would be the arctangent of the imaginary part over the real part. So that's fairly straightforward to get our hands on then in this math model. And then what we're going to do is we're going to do a small argument approximation. We're going to assume initially that the numerator is small compared to, AI. We're going to be assuming that AI is much less than AC. So the interference is not overwhelming. It's a weak interferer. Or I guess I've written down here, AC is much greater than AI. So we want to get our hands on phi in that case, and phi will approximate out if we go through what's going on in here. We're looking to get phi, and we have that expanded out up above. And so if we have the small angle approximation, what we're able to do is say that the arctangent of x is approximately just x, and the expansion is based on assuming that x is much less than 1. So I know this seems kind of fast, like how did you do all of that? Well, we're just going to get this term right here. That's what we're going to get. AI, and then we're going to get the dominant term from the denominator is AC. So we're effectively getting AI over AC, because we're saying, oh, by the way, since AI is much less than AC, we'll just keep the only term in the numerator and the smallest term in the denominator, and then put it back together into terms of the received signal, envelope and phase, and we can see what we've got in the argument now, AI over AC sine omega IT. So the discriminator will recover the derivative of that argument for, let's see, FM modulation, and then when we integrate the derivative, we get back to what we started with. So we'll be recovering within the gain constant of the phase demodulator just what we see in the argument already, and then the derivative will pop up when we do the frequency modulation case. The bottom line is we're seeing that the interfering tone appears directly in both the phase modulation and the frequency modulation case. And we're seeing something also that's rather interesting, and that is that, and this is something that I'm going to come back to and kind of bring to your attention, that put two colors around it. For FM modulation, the amplitude of the interfering tone is proportional to the offset frequency, Fi. And that's because when we take that derivative, we're getting this Fi that pops out when we take the derivative of the phi. And that is kind of bad news. What it actually says is that as the signal gets further away from the carrier, it actually has a more impactful effect on in terms of producing an interference that we're actually going to notice, because it gets stronger the further away it is. But if we have a bandpass filter at the front end of our receiver, we can reject that interfering tone. So we're going to assume that if we have a bandwidth W as the bandwidth of the message, then following the action of the discriminator, we've gotten rid of that. It's gone. So that's good, but it also tells us that there is a trend, and that will be when I want to refer to noise here in a little bit. When AI is similar to AC, in other words, the interfering tone is about the same amplitude as our signal of interest, then the analysis doesn't hold anymore that we just went through with this guy over here. This was an expansion, a power series expansion of arctangent. And you probably can remember that from calculus somewhere along the line, that power series exists. So we have to use the full arctangent, and it's kind of beyond the scope of the class to get really intimate with it, but I am going to give you some pictures of some modeling I did of this. I actually did it in Mathematica quite a few years ago just to put in the notes. I just played with the equations and wanted to see what the arctangent does. It's not a hard model. All I was really doing was just plotting this and the derivative of that when I would put in different values of AI over AC. So if I put AI approximately equal to AC, I'm looking at, well, I'm starting off with, let's see if I can get the right color here. Starting off with the interference 1/10 of the carrier strength, and both phi and the derivative of phi look pretty good. They look like reasonable sinusoids, like we'd expect. If I set AI equal to 0.9 of the carrier, now phi that we're recovering from the equation up here, just taking the arctangent and plugging those expressions in, starts to look very distorted, and the derivative starts to look pretty nasty because there's these inflection points going on. What's getting that so exciting is that stuff that's happening right in there. That rapid change from positive to negative is giving a negative spike, kind of like it's producing a delta function. Thinking back, if you take the derivative of a step change, then you get a delta function. So we're getting a negative delta function in this case because we're going from positive to negative. And then if you take it up a little bit further to 1.1, it continues to get worse, and now in this particular case we're getting positive spikes as well as some negative stuff, or at least that's what my numerical derivative in Mathematica said. And I think it's, I don't know, I'm pretty sure it's right, but the bottom line is you get something that in a further chapter of the book, I think it's chapter 6, let's see, 1, 4, 5, 6. No, 6 is probability, 7 is random processes, 8. So it's in chapter 8. There's a discussion about this, and these positive or negative spikes that are occurring in the discriminator output are called clicks, and that is what happens when the interference levels become close to the signal level. So the signal basically gets, the demodulated signal gets destroyed, or the nicer sounding term is lost. So it gets lost. And remember, in amplitude modulation, if we were using an envelope detector, when the interference got powerful compared to the signal, it would also get destroyed. For the coherent demodulator, though, it just gradually takes over, it doesn't have this thresholding phenomena. But a discriminator has a thresholding phenomena. And the very last figure I'm going to show for this chapter, we'll see that. Actually, because I'm on it right now, I'm going to go take a quick peek at it, just because it might be something that you can think of later. So this is the general characteristic of all the modulations we've looked at so far, and I'll probably look at this again, but as the signal-to-noise ratio at the input to our receiver, which is a more general measure than just simply signal-to-interference ratio, it's just saying signal-to-noise in general, is below a certain level, like we have a lot of noise in the background because our signal is weak, double sideband, single sideband, and coherent demodulation, QDSB, which we'll be looking at, but they just gradually are such that the output signal-to-noise ratio in the detector just gradually deteriorates. It gets noisier and noisier, whereas FM, which is shown in here, reaches this point where there's this knee, where once you get below that knee or operating point, things just deteriorate very, very rapidly. And I'm willing to bet that everybody's observed this. If you drive and listen to FM radio in the car, it's very noticeable as you're driving, say, from Colorado Springs to Denver. You go up Monument Hill, and then you are going along on that section called Greenland, and in that area is when the stations start to disappear because we just don't have a good enough line of sight to the transmitter anymore, and the signal kind of fades in and fades out. Then usually it just, bam, it's gone. Anybody observed that phenomena before on FM broadcasting?
Usually it lasts all the way up to Castle Rock.
Okay. It depends on what you're listening to, though. The station you're listening to, you're really noisy, Chris, in the background. If you're listening to a station that is clear channel, in other words, is not replicated, is not occupied by Denver, then I guess I could agree with you. That would be true. Usually what happens, though, is you get to the point where you've got a station in Denver that's occupying the same frequency as in Colorado Springs, and then it sort of snaps between the two for a while, and then it just snaps onto the one that's strongest. But on the flip side of that, if you were driving out east on, say, I-70, listening to, I'll just say, a Rockies baseball game as an example, because I've experienced that with my family. I think it's KOA out of Denver. The signal just gradually gets noisier and noisier, but it doesn't just all of a sudden disappear. It just sort of slowly sinks into the noise. And that's the blue curve that we see here. So it's a trade-off as to what you want, but you can see that the FM modulation, when it's there, its signal-to-noise ratio is far superior to the double sideband and single sideband. So that's kind of the trade-off. But we already know one of the downsides of FM broadcasting is it's going to occupy more bandwidth, and that's indicated by D being the deviation ratio. So the bigger the deviation ratio, the better you do, but you occupy more bandwidth. I probably said too much about that, but I was kind of excited about making a point, so hopefully that made a little bit more of a point. So that's what's going on, and the basis of that is the beginning by studying the tone jamming idea that we were looking at up here. So what I want to do is use that as the basis for a little demo that I have at the tail end of the Chapter 4 Jupyter Notebook. So in this particular case, what I've done is I'm putting in a carrier. I'm doing this at complex baseband, so just like in what I was doing in the notes, I'm just saying, I could call that AC. I'm not sure where I called it 1 because I have AC defined up here. I'm saying AI is equal to 0.01, and I'm just at this point going to simulate that, I'm doing 10,000 samples per second, and I'm ranging up for 1 second. So I'm going to capture 1 second, and then I'm going to plot the power spectrum, and I'm just looking at the signal, the received signal, I haven't demodulated it yet, but I'm looking at zero frequency is just the pure unmodulated carrier, because this is complex baseband now, and then sitting above that is my interfering tone, which I've got set at 100 hertz relative to this 10 kilohertz sampling rate. Now I go into this complex baseband discriminator that we've looked at before. The model for that is further up the page in the notebook, and just plot the output, and we can see that what we're getting for the output is that interfering tone at 100 hertz in this case. And if I go ahead and just plot the spectrum of that tone, I'll see that it does have harmonic distortion. It's not awfully bad, but it is definitely noticeable. But now what I'm going to do is I'm going to change the ratio. I'm going to keep the unmodulated carrier, and I'm going to turn up the jammer. So I'm going to make the jammer be 0.1. And in the spectrum, you'll just see that this interfering tone is risen up closer. But now we're starting to see some asymmetry like we saw in the mathematical plots I have in the notes. I don't know if your eyeball is picking it up, but the top of the cosine wave is kind of fat. The bottom is kind of getting narrower. And if I go look at the harmonic content, it's getting far worse. This is not our message, this is our interference, but the interference is just sort of taking over the discriminator at this point, is what's happening. And the interference in the information that would be on the modulated carrier, if I was to put that in here, would be getting swamped out and kind of getting destroyed by the interference. If I was to take this up to 0.6, let's say, now we can see it's even stronger. It's not greater than, but it's stronger. And now we're starting to get a very non-sinusoidal output for the interference, and of course the spectrum analysis of that will just show lots of harmonic content that doesn't roll off very rapidly. So for whatever it's worth, that is just kind of a little demonstration. You could do more with that by putting a sinusoidal tone at a lower frequency to represent the message, and then just see how it gets gradually destroyed by this interfering tone. But what I want to do next is do something that's not really in the book, but kind of to get you excited about the next topic in the notes, and that is I'm going to design a quick Butterworth filter, 12th order, give it a cutoff frequency of 1000 hertz, and I'm using the same signal that I have up above. So I'm just going to generate that spectrum, filtered complex noise that's been filtered by this low-pass filter is what we're doing here. I'm generating Gaussian random numbers of unit variance, real and imaginary part. And now what I'm going to do is bring back in what I had up above, and that was WR, or XR I mean. So I'm going to take this back down to 0.01. I don't know if that's what I wanted or not, but it's what I had when I was playing with it earlier. I'm just going to make the interference. I'm going to consider now just a much weaker interference, but what I want to do is look at what I'm going to get at the output here. So now on my receiver front end, because I'm adding noise in, I'm seeing this band limited noise across here. The roll off of the noise is from the Butterworth filter. My unmodulated carrier is here. My interfering tone is here. But now when I go look at my discriminator output, which is not what I wanted to do. What did I do wrong here? Oh, I have to rerun the discriminator. let's see, I have to go up here and I have things tied together, so I have to do that in here, I think. I may have to do something different. That's not exactly what I wanted. Although it seems like something I saw just a little while ago. No, that isn't what I was doing before. I changed something from the way I had this set up before. I wanted to look at this, and then I wanted to look at the discriminator output. So I think what I need to do is I must have deleted a line of code or something. I believe what I need to have up here is running the discriminator on not XR, but on XR plus WF. So it's the combination of the noise and the received signal. Okay, I think that's what I had, or that's what I wanted to have. I'm going to get rid of this, rescale this. So what I'm after here is to say that that is the interfering tone. It's not very powerful, but the important thing is to see how the additive noise, which is influencing this right in here, is causing this increase in amplitude, in spectral amplitude, as the frequency goes up higher and higher. So we're seeing that linear increase factor that we saw over here, that I circled right there. As you move up with your interference to a higher and higher frequency, it actually grows in amplitude. And I could simulate that, I think, maybe a little bit better. Here you see the tone is right down here. If I would move it up to, say, 300, you'll see that it will rise up with the noise background too. So I'd have to change that up here to 300, rerun it, add noise to it, and then the tone is up further in frequency now. And now we'll just look at the spectrum at the discriminator output, and we'll see the tone is sticking up even further, and the noise is right there along with it, sloping up in frequency as you move further away from DC. So this is what noise does in a receiver front end. The jammer also increases, but if I was to just take away the jamming entirely, we would still see that the noise amplitude gets bigger when we move further away. So I just made the jammer tone really small. Look at that. It should be now buried down inside the noise. Yep, it's sitting below the noise floor right now, but now we look at just the discriminator output, and we're seeing this sloping upwards effect. Essentially no noise, and this is a decibel scale, essentially no noise at really low frequency. Our message would get through, but we're going to have this ever-increasing background of noise as we go up higher in frequency. And this is just looking at the waveform. Now I know why this worked before. I skipped over this spectrum and I ran this plot first, but what I'm getting after right now is that an FM discriminator output, noise increases the higher the frequency is. So if you were to listen to an FM receiver without having a special processing block known as a de-emphasis filter, the noise gets more powerful higher up in frequency. So you hear there's this really high frequency noise, and you don't hear as much low frequency rumbling, and that's just the nature of how noise influences the spectrum. And this is a topic that's not even covered in Com Systems 2, but it is in the book, and I think, yeah, I guess I have a good enough picture in here. Yeah, I have a good enough picture on the next page. So I'll just flip back over here to the notes though. So now we're talking about how we saw with the tone jammer, and we're seeing with the noise in the Jupyter Notebook that the interference is proportional to the frequency of the jammer, or just with general noise, we're seeing that it was tending to be something that looks like this. As F gets up higher, the noise at the output of the discriminator gets bigger and bigger and bigger. So what is done is to do something called pre-emphasis and de-emphasis. I know when you don't hear an FM station on the dial, when you're just tuning around, you hear all that noise, and that is the kind of noise we're talking about, but that noise has been shaped in such a way that it tries to roll it off at the higher frequencies. And the way FM broadcasting does that is it pre-emphasizes or boosts the high frequencies. And it's doing that to overcome the increased noise background level at the higher frequencies. So that you can't get rid of the noise. It's there due to the physics in the receiver front end with the noise, but you can let the message signal broadcast at a higher level in those higher frequency bands. And then what you do at the discriminator, you gain flatten it or gain equalize at the higher frequencies. So the picture of how that works is end to end, what you're trying to do, this is the discriminator output. So if you don't put the de-emphasis filter on, what happens is the noise just gets bigger and bigger. That's the blue curve. But with the pre-emphasis and de-emphasis filter, you're able to flatten the noise down. So in FM broadcasting, this is what it looks like in an analog circuit sense. Digital signal processing can do the same thing, but you would boost the high end at the transmitter, and an example of a RC circuit is shown there. And then at the receiver, you would put in a simple low-pass filter that would roll off the pre-emphasis, so it would take noise down and then take the high-frequency signal down to sound consistent with the low-frequency information content. And for FM broadcasting, the time constant that's used is 75 kilohertz. So the time constant is 75 kilohertz. Or microseconds, I mean. So you're boosting starting at 2.1 kilohertz. That's this guy right here. And then you just flatten it out at 30 kilohertz, which is, way above our human hearing. But that's just the design of the circuit in the olden days. And the Federal Communications Commission designates this as the way FM broadcasting is to be done on the FM broadcast dial or spectrum portion. You pre-emphasize and de-emphasize. This technique for masking noise by putting signal further above it, which is what we're really doing, is used in two other mediums, but the two other mediums are very uncommon these days. Some of you may have one or the other of these, but I'm guessing most of you don't have either of them. Does anybody want to take a guess at what these other two mediums for audio entertainment were? And maybe still are, I don't know. I know one of the two is still popular, but not very popular. Does anybody want to guess? Okay, you don't feel like guessing today.
Does the medium, is it kind of, are you saying it's like a physical medium, like discs and stuff?
Yep, exactly.
So there's cassette, right?
Yep, tape.
Yeah, tape. And then is the other one like the it's like the bigger DVD. It's
well, the LP, the vinyl record.
Yeah.
And that's
that one.
Yeah, you have those, or you own some?
My sister does.
Okay, I've got a
I've
huge
heard they sound nice.
yeah, I've got a huge collection of them in my basement. I worked at a radio station when I was in college, so I got to buy a lot of
That
records
sounds
at a
like fun.
discount. Yeah, I was actually the engineer, so
Dude, I
you
wish. I
remember
like audio stuff.
you remember me talking about the bootleg FM radio transmitter that I had when I was in college? I was the person that built that. And
Nice.
then I nearly got, well, I told, didn't I tell this story a while ago? Maybe
No.
not. Okay. The dean of students called me and the radio station manager into his office and said, you guys have to cease and desist, otherwise you won't graduate. So I had to cease and desist, and it was our competitor radio station across the street in a different dormitory that turned us in. Wouldn't you know it? I mean, they didn't like our competition. So, at any rate, I
That's good.
yeah, it's a true story. I can tell you that much. The transmitter is still sitting in my basement here, because I had other people that wanted it after this happened. The station was pulled off the air, and then other people wanted to start it up again, and the dean of students said, if your equipment shows up in anybody else's hands, you're going to be held responsible just the same. So I learned my lesson, but I don't feel that bad about it. And there's an antenna sitting in the attic of a dormitory up in Upper Michigan, which I'm sure is still there, because I never went back up there to take my antenna down. That was the transmitter antenna. Yeah, I did have fun doing it, and I wasn't. My station manager was a mechanical engineer, so we got along well. We actually played in the band together too, so we were in pep band together, so we had musical interest for sure. So pre-emphasis and de-emphasis is was used in the olden days for vinyl recordings. Pre-emphasize the high end so that when you play back, you can mask over some of the noise that comes about in the mechanical playback of the needle that sits in the grooves on the vinyl LP. And tape, magnetic tape, which was cassettes and things, very popular for a long time, had the exact same issue, and that was due to magnetic recording and then playback that also had an issue with noise more predominant at higher frequencies, and they solved that using the same idea of pre-emphasizing and then de-emphasizing. So if you were a tinkerer like I was, you would build a receiver or build the phonograph preamp or whatever to play your music, and if you didn't put this low pass filter on that started to roll off at 2.1 kilohertz, you would listen to it and it would sound really tinny and very high frequency strong. Until you put that filter on there, it didn't sound natural. It sounded really pushed, like you had the treble turned up all the way. It sounded very whacked out. But maybe you like listening to music with the treble turned all the way up, and that's kind of what it sounds like if you don't de-emphasize, because it's put on at the transmitter, and they do that all the time, so that's the way it is, and it's your responsibility in the receiver to put the de-emphasis in. Not a lot of math there, just if I ask you a short answer question, what's the purpose of pre-emphasis and de-emphasis in FM broadcasting? I want some discussion about these paragraphs in here, that it's designed to help with the noise at the higher frequencies in the message. They're getting covered up by the boosting of the noise, so you boost the audio up on top of it, and then you take both of them down, and essentially you're pushing the noise down further because you put the signal way above it. It works well. It's old-fashioned though. Okay, the next topic is multiplexing, and I want to spend just a little bit of time on this because I'm thinking about, do I step into this domain for this exam, or do I hold off on this till the final? So I want to see how it goes, and then this is going to lead to my software-defined radio demo, and then we'll jump over and do quiz, or at least one page of the quiz, depending upon what I think here, and then also look at some old exams. So multiplexing is something that we looked at the end of chapter 3, time division multiplexing, and that was where we could send, in the olden days it was analog multiplexing, pulse amplitude modulation, but multiplexing in the time domain nowadays is most typically thought of as being digital multiplexing. So bringing different digital streams together through a multiplexer and then sending them through a common pipe. Another type of multiplexing that we can have is frequency division multiplexing. So with frequency division multiplexing, and this is extremely common, it's used in cellular telephony, satellite communications, was used in wired telephony until TDM, time division multiplexing, took over. But FDM is you locate groups of messages on different subcarriers and then sum them together to form a baseband signal. So this block diagram pretty much explains what's going on. You have message 1, you let it modulate a subcarrier, so you've got a number of subcarriers, and all the way down to subcarrier N, and each of those modulators could be the same kind or they could be different. So you could have different combinations of modulators. The messages could be analog or digital combinations. And the idea is you're going to sum all of these modulated subcarriers together in such a way that the spectra of each of them don't overlap. So I think I've got, don't have an exact picture on the next page, but if I was to just draw a single-sided spectrum right here, what we'd be talking about doing is we'd have, a signal at FSC1, FSC2, FSC3, and this is 0. And then, of course, it's got the mirror of that on the negative frequencies. And then those signals are put in together, they're added together. So in a sense, they're all one giant signal now that's just blocked by that blue passband, low pass passband. And then that goes into an RF modulator that modulates it a second time onto the super high frequency carrier. So a lower bound on the composite signal bandwidth for this scheme would be the individual bandwidths of these signals. So you've got W1, W2, W3, so you just simply add those up, and that's going to be the baseband bandwidth. And then if it's an AM modulator, it's going to be twice that baseband bandwidth B. If it's an FM modulator, it's going to be Carson's rule, and so on and so forth. So when you get to the receive end, though, then you have to tear this apart, do everything in reverse. So at the receive end, you RF demodulate using whatever scheme was used in the RF modulator. So it's AM, single sideband, FM, whatever. And now you break the signals apart, generally with some sort of filtering so they don't interfere with each other and create a nearby signal that can cause some interference. So you might separate them with, say in this case, 3 bandpass filters, and now you have your subcarrier demodulator sitting there, and then you eventually get back the individual messages, analog or digital. And the modulation schemes are just a mixture of whatever you feel is appropriate. The RF demodulator might be FM, subcarrier demods 1, 2, and 3 might be amplitude modulation or single sideband or something like that. In the earlier days of wired telephony, single sideband was what was used for the subcarrier modulation, and that is what you played with in project number 1. So that was kind of a simplistic version of what was done in wired telephony, where you'd put all the individual messages up on subcarriers and then at the other end they would get taken off, and they would actually relay all those signals over microwave towers. So they would modulate the subcarriers using FM, I think is what they used most often, onto a carrier, and then at the other end of the tower they would demodulate it and then do what they needed to do before they sent it on further across the country. There was a network of microwave towers that relayed information like that all over the country. Nowadays, we don't use that anymore. We use fiber optic cables that are buried underground, and things are done much differently. But the idea of subcarriers is still heavily used today. So I wanted to just look really fast, and then I'm going to jump over to the software-defined radio and just let you see that FM stereo broadcasting is exactly an example of frequency division multiplexing. It is a different hybridish combination of things, and it is what it is because FM stereo came well after FM broadcasting got started. I think it was like 1948 or something like that. I don't know exactly. All I know is I had a grandfather. I grew up near Green Bay, Wisconsin, and my one side of my family was from the Chicago area, so I got to visit the big city of Chicago very frequently to visit my grandparents down there. And my grandfather was a really big music guy. He really enjoyed symphony music in particular. So he'd have his listening room in the basement, a lot of homemade electronic amplifiers and speakers, and I don't know, it was really the deal. And FM stereo broadcasting was very big in Chicago because it's a big city just like Denver is, so there were lots of FM stations, and he would always call it by its original name, and that was FM multiplexing, or multiplexed FM, because I think that's what they called it when it first became well known. It was referred to as multiplexed FM, or FM multiplex. So, and it's an example of a legacy system, because in the beginning that was all the information that got modulated onto the FM carrier. It just went from 0 to 15 kilohertz. And then when people said we need to have two-channel sound, they said, okay, we'll augment this by putting some subcarriers up. So they put a subcarrier up at 19 kilohertz. It's called the pilot carrier. And then they double sideband modulate another information channel and center that on 38 kilohertz. Now, what they do then is they're sending left plus right on the baseband spectrum, and that's what this block diagram is showing you. We have a matrix. I call it a matrix. It's taking the left and right program sources and matrix, running them through a matrix in a sense. It's a 2x2 matrix, but 2 in and 2 out. So we form the left plus right, and that goes on over here and gets put in right at baseband, summed in into the FM modulator. Then we form the difference, left minus right, and that is this guy right here, and that gets multiplied or placed up on a 38 kilohertz subcarrier using double sideband modulation, and then that gets summed in into the composite baseband signal path. And then the third signal is the 19 kilohertz pilot, and the 19 kilohertz pilot is directly related to the 38 kilohertz subcarrier. So what is the pilot used for? If you were a navigator, you'd say, I know what a pilot's used for, but I mean what a pilot is, like in a ship canal or some riverway thing or another. You'd have a pilot to help guide you through a difficult passage. Somebody would jump on board and pilot your ship through the channel or something. So that term pilot is the same thing that's terminology that's used here in the communications world. The pilot is a reference that we can use to take the signal back apart again. So it's guiding.
Can I ask a question?
Sure.
So I'm looking at the diagram for the left and right because that's actually something that I've been curious about.
Okay.
So you frequency multiply either the left or the right so that they have two different independent spectrums, and then you have a demodulator at the end that's looking for two different frequency bands. Is that right?
Kind of. We don't multiply left and right together, though. We add and subtract them.
Well, yeah. No, we 2 times frequency multiply the right carrier with the pilot signal.
Okay.
So that it's at a different frequency spectrum than the left. That's why there's 2 different humps. Right?
You're talking about in the picture down here in the middle, the spectrum.
Yeah.
Yeah. There's two different. There's 2 different subcarriers. There's 3 subcarriers. One that's unmodulated. That's the pilot, and then there's the left plus right at baseband. Starts at 0, and then there's the double sideband up at 38, centered on 38. But this operation here is like what you have on your RF board that you used in the lab. This is
the frequency doubler.
Yeah, that's a doubler right there. So the point in having the doubler, though, is that by sending the pure 19 kilohertz pilot, you can use that to demodulate coherently the left minus right subcarrier. So that is used directly down here by doubling after you bandpass filter, or this could be a phase lock loop application as well. Lock onto the 19 kilohertz pilot, then double the frequency, and then you have an exact phase coherent carrier for demodulating the subcarrier at 38 kilohertz. I think you said it about right, but I want you to make sure you get your terminology correct. I don't know if this is exciting to you. To me, it's pretty exciting. I mean, it's not.
I like
it's
it.
1948. Think they invented this back in 1948, and what they wanted to do was create an overlay on an existing standard. And that way, if you have a cheap FM radio, you just get the left plus right, and you don't have the capability to do what my grandfather called FM demultiplex. He would always talk about FM demultiplex. And the big cool thing for me when I was growing up was if it's a signal containing stereo, there's a little light that comes on the receiver that tells you it's a stereo signal, and that light comes on because the pilot's been detected at 19 kilohertz. I don't know if, that was intriguing to me, the pilot, it's there. But then I have to do something with the pilot, and I have to go look for demodulate the subcarrier. And then you D-matrix, you rematrix the left plus right and the left minus right to get left and right. In Lab 6, you do this all in software. So you get to do all of this with the software-defined radio, because you will get these raw samples out here in complex baseband, and then you write the code to do all of this stuff. Not in real time, you do it after you've done a capture, and I think Daniel was sending you captures as of yesterday, I'm thinking. I want to show you some captures right now, though. I want to spend more time on this, but I guess my biggest thing is, do I want to do anything with frequency division multiplexing on this exam? I know you'll see them on the old exams, and it's also on one of the quiz, the second page of the quiz. We don't have to decide that right now, but I'm going to come up with this question. If not, this is going to be a dividing line. So, this is kind of a dividing line. Do I allow this section in, or do I just hold off on that and save it for the final? I'll come back, and we're going to make a decision, though, today before we leave class. Everybody got that? You can vote. Will can't vote. He's not here, but we're going to carry the vote without him.
I'll take his vote. I think I have his best interests in heart.
Okay. I believe you probably do, because you guys are good friends. Okay, so it's pretty cool the way it works, and there's a lot of other things that go on here, and we're going to go look for those other things. There's more than just a 38 kilohertz subcarrier. There's something called RDS sits up here.
Professor,
Yes.
a question. Do you know if they added this stereo information to FM after they moved the FM band up?
I'm not good in that part of the history. I don't know what the
Okay.
FM band, you're talking about when Armstrong first started FM
Yeah.
radio?
Yeah, it was much lower, and then he got into a political
Yeah.
battle with CA.
Yeah,
and
well,
they
it
moved
was little guy, big guy versus the little guy, and they destroyed him,
Yeah,
right? He actually
did.
died, a poor man, and
he jumped out of a window.
yeah, it's
actually,
it's a
committed
very
suicide.
sad story.
But the best part is his wife got most of the money out of RCA years later.
Oh, really?
she won all the lawsuits,
Okay,
evidently, because they stole his circuits.
I
is
know,
what they did.
I know. They were jealous of him.
but-
He was
yeah.
a smart man, and he died. Don't be an engineer like him. He was
Yeah, he was
famous, and
stubborn.
then he crashed and burned because greed got the better of somebody else. But and they took him
Yeah.
down.
It was kind of sad.
There's stories like that
Okay,
today.
just wondering.
Yeah. So what I was going to say, there's another subcarrier up here at 78, and I think it's 76, 77. No, it's the third harmonic of the 19 kilohertz, or is it the fourth harmonic? Yeah, it's the fourth harmonic, right? Yeah, I think that's right. I think it's at 78 kilohertz, and RDS is
Can I ask you a question?
yeah.
Why are we setting the pilot frequency so low?
Ask the inventors, whoever invented.
Okay.
I mean, that's just what they decided to do. It's legacy, though. We don't change it. The only thing that's changed in my lifetime majorly is TV. Right? We had analog TV, then we totally trashed it and came up with digital. But FM radio broadcasting has not changed. It's just a legacy. There is the overlay, and we're going to see that in a second too, for HD radio, which overlays. So I'm going to jump over back to this, keeping my eye on the clock because the time is going to fly by here. And I've got my RTL SDR plugged in here. I put it on the camera, but I don't want to unplug it, and it's on a dongle that's too, I can't stretch it over to get in front of the camera. I do have a picture of it though, so I guess I can do that. I've got Lab 6 up here right now. This is Lab 6. There's what the dongle looks like. I have a more expensive version of it that has a temperature, a higher quality crystal oscillator and a lower noise front end in it. This one right here costs $20, and the more expensive one costs $30. So that's plugged in, and then I can go over here, and this is Lab 6. I can go into Documents, and I have SDR Sharp on here, which is a free application. It's the first way you can start playing with this. So when you bring this up, we have this nice GUI application, and this is KCME, Classical FM in Colorado Springs. It was a little bit loud, right? You guys still there?
I can't hear it.
You didn't hear it?
Can't hear nothing.
Okay, I'm gonna go unplug my headset so you can hear it on the speakers. Probably that's where you heard it. Now it kind of fell down into the noise, so.
So is that dongle implementing the circuitry or the block diagrams you had pulled up earlier?
Yep. It's well,
That's
the
it.
software part it's being implemented in code, but does anybody know
But it's
that?
a hardware receiver.
What's that?
It's a 5-volt hardware receiver.
It is, yes. Well, then the rest of the
Okay.
receiver is in the software, though. It doesn't. It was designed to be a TV receiver in Europe for HD TV in Europe, and then it was repurposed by hardware hackers to be used for programming your own receiver. And people have done a lot of different things with it, and this is just one of the apps. But we can then bring this closer to home so we can get inside that signal. And I wanted to point something out to you, but it's closing, so I'm going to show it to you in Python. So I have a notebook over here, RTL SDR1 demo notebook. So in this notebook, I've loaded in another part of Scikit DSP.com called the RTL SDR helper, which interfaces to this radio device in particular with its drivers. And then I can do a capture. So right here, I've got a function within that module called capture. I'm going to capture for 5 seconds. I'm going to capture at 88.7 megahertz with a 2.4 megasample per second sampling rate, set the gain, and it's capturing right now for 5 seconds. And then I can go ahead and plot the spectrum. Well, here I can do two things. I can save my capture if I've done the next step down below here. Here I'm going to take my capture and restore it from a complex form. Here I'm going to take a capture in the X array here, which is this array right here, a complex array, and save it in a WAV file. And the WAV file is perfect because it can store stereo, so I'm using it to store real and imaginary streams, which makes me, repurpose it. But I'm not even going to do that right now. I'm just going to simply look at the spectrum of what I just captured. And there it is. This is my broadcast spectrum right in the center. This is some other signal. This is some other signal over here. These rectangular shaped blobs that sit above and below it are part of the overlay spectrum called high definition FM radio, or HDR, HD radio. And that's a proprietary standard, but that holds digital programming information, and it can hold multiple channels, and it does not interfere with the existing FM, which sits in the middle. And the FM that sits in the middle holds all the multiplex standards and all that other stuff. So the latest add-on is to have this HDR standard, which puts information in upper and lower sidebands to spread it out a little bit further. And my car has an HDR receiver that is part of most new cars today. They'll have an HDR radio, and KCME in Colorado Springs has got both a rebroadcast with higher quality sound of the classical, and then it has the jazz station is on a second channel. So they can put multiple channels up in that digital part. But if I want to go a little bit further, I have a mono FM receiver that's in this package. So I just demodulating now my 5 seconds, and I can take it all the way down to audio I can listen to, but in the interim I can also look at the spectrum of the baseband after I've done some additional processing, things that you learn about in Lab 6. So let's take a look at that. And so Colton, maybe you want to tell me what we're seeing right here. This is frequency in kilohertz. I should have written it out that way, but so from zero, this area, what does this area represent in terms of the demodulated signal components? What's in this region?
Is that L minus R?
It's L plus R. So this is the
Oh, right, because L minus R got the frequency doubler.
Yeah, we were just listening to L plus R when we did this mono FM demod. Here's the 19 kilohertz pilot, right?
Yeah, the pilot, and then L minus R.
Is up here at 38 as double sideband, and then we
It's not as clean as it looked in the other picture.
before I refreshed it. You mean?
No, the from in the notes, the theoretical
Yeah, that's an
passband.
idealized picture, though. Well, let's see what the program is that was playing when we demodulate it. So that was what we were listening to before. That's part of the planets. If you ever listen to classical music, that's Gustav Holst, a composer from England. He did the planets many years ago. At any rate, you see a little blip here and another blip up here. So this is the RDS blip. It's actually at 57. Let's see. Yeah, 3 times 19 is 57. So this is a little data spectrum subcarrier that contains what's called the RDS, Radio Data Service. And that's what gives you program content notes, like what's the call sign of the station, what particular song are they playing, and any other things they want to stream up into that low digital bit stream goes in there. And then this is yet another subcarrier that's up even higher, I guess at 78. I don't know what this is. This might be proprietary. It might be a data link that goes between the studio and the transmitter up on Cheyenne Mountain to relay information or other things. But it's kind of like being a detective when you see the baseband spectrum with all the subcarriers visible. That's about all I'm going to do on that for right now. When you do Lab 6, though, you're going to be playing with these captures that Daniel has made for you. And you could go look more at the other stuff. I'm way running out of time now. So the quiz, I'm going to glance through the quiz, and then we're going to make a decision what we want to do with the remaining little bit of time. I have no problems supplying you with a solution to the quiz, but there's 2 pages. There's 2 problems on the first page. One is a phase lock loop, a first order phase lock loop question. Second one is a synthesizer with the offset oscillator, and this follows exactly what I had in the notes that we went through on Tuesday. And then the part B quiz is an FM multiplexing and then drawing the block diagram of the receiving system for these subcarriers and kind of drawing it to standards. I'm getting more interested in saying that I'm not sure I want to push this far for this next exam, but it's definitely going to be on the final if it's not on the next exam, and I'm fine either way. But
Can I say my piece?
Sure.
Or Will's and my piece?
You're going to vote right now, right?
Yeah.
Okay.
I'll put my vote in. That's fine. If we haven't even had a chance to review the material in the context of styles of questions we can be offered,
Right.
don't put it on an exam.
Okay. Well, you do have
Considering we're
examples
just now
of
seeing
in
it.
the old exams, though. But I understand what you're saying. It does appear in both of these old exams.
Now, here's a freaky opinion. I would take that over PLL.
Well, PLL is going to show up. So you can see it's on an old exam right here. But I think probably at the end of this, here's a multiplexing type problem, but I can pull those off. Let me just see if I had that on the other old exam here. Yeah, here it is. If it eventually gets into focus. So here's another frequency division multiplexing type problem where I have you draw the block diagram of the receiver. I'm fine though. I'm used to being able to spend good quality time on this, and I would like to spend quality time on it, but I also would rather just go through the phase lock loop problem and the other synthesizer problem because that came first, and we can save it.
Please do.
Okay, anybody else you're going to let Colton carry 2 votes and no other voting, or does somebody want to Slack message into me what your feelings are?
I got to jump in. Go ahead, John. You can go first.
I was just going to say that if you put it off to the final, that's fine with me. I already feel like Alice Lost in Wonderland when it comes to PLL. So I gotta do some studying on the weekend.
And
It'll be
Jared,
tough,
you're also
so.
there. I think at least you were there. And somebody else just messaged me. Get on the right channel. Yeah, Jared agrees.
I speak for the people.
Yeah, that's fine. That's what we're doing. I'm being, the benevolent dictator that I'm allowed to be.
Well, as long as you don't just absolutely crush us on the final by adding more content.
The
That's my
final,
only.
if I go, the new material we're going to have from the appendix is very easy and straightforward. So I got to have something else on the final that you haven't been tested on yet that's a little bit more involved. And it's still not really all that involved. So let's go back over.
I still have nightmares of what you did to us in modern DSP final. So
Oh, well, yeah, that was exceptional, I guess, but let's not try to go back and repeat history is what you're saying. So,
yeah. Well, and then also we have another project we're still coming around on, right?
yeah, and I'm working on that, but I decided I wanted to do this SDR demo because I know the lab is ramping up on it. So I can look at old exam problems, or I can go through the quiz problem, which you don't have the solution.
Let's start with the quiz.
Okay. Okay. I'm with you.
Considering the exam does have a solution.
Yeah, well, the quiz has a solution, and I can work on it right now. So this is the phase lock loop, closed loop transfer function. So what you would have on your crib sheet, and let's just go through the guidelines for the exam before we get too far down the pathway here. It's going to be open book and open notes, not a problem with that. I'm going to want to have you guys keep Slack on, and I think I'd like to keep the video on. That was a discussion we had in our faculty meeting. I think Slack is probably more important so that you can be messaging with me. And I may be pinging you individually just to make sure you're awake and you're still working on the exam, because it's time limited and you don't have time to goof off. But
By the way, Mr. Wickert, or Dr. Wickert, so I use the mobile app, and in order to get good resolution on the video, I have to be in the call. I can't be in a call and answer Slack messages at the same time
okay,
because I have to close the video to answer messages.
okay. Well, like I said, Slack is going to be more important because we can communicate that way. So if I decide I want to just individually message you kind of at random to know that you're still there and you're working, or I can just say any questions, I want you to respond to me. So when I say please respond, okay? Everybody got me on that? I'm going to put my headset back on so I can hear better. So, but I would still recommend you making a crib sheet. So I would make a recommendation that you make a crib sheet, look, two-sided sheet. I mean, you can make an n-sided sheet if you want to, but just something that has the high points in the material. And the material is going to be everything since the last exam. So it's going to be things with single sideband, all the way through the topics of time division multiplexing in chapter 3, and then into all of FM up through the point that we were just looking at, where we come out of pre-emphasis and de-emphasis, but we don't go into anything with frequency division multiplexing. And it will be of the style that you're seeing like here in this quiz problem, and of the style that you see in the old exams. But of course the old exams covered more material. I think the exam was run later, so anything that you see from the appendix A will not be on the exam, and anything on frequency division multiplexing will not be on this exam. So just be aware of that. I think that takes out at least a page on each of the old exams, if I'm not mistaken. So you will be responsible for a problem like this, and if I just start working on this problem, this is a first order phase lock loop, so you should look at this. If you had this on your crib sheet, you would have something like first order phase lock loop, and this is really the only phase lock loop that I'm holding you responsible for and doing any math with, is the first order loop. That's what its closed loop transfer function is. So what we learned about from the first order phase lock loop when we were first studying it is that the lock range is running from kt minus kt over 2 pi up to, let's see, this would be, I have to change this a little bit. I get too used to my Apple Pencil where I get to double tap it and then the eraser turns on, and this is not an Apple Pencil, so I did the wrong motion and it didn't work for me. So this would be F minus FC. Get this to go back on again. So the lock range would go from 10 megahertz above and below the center of the lock frequency. So I say, given that the center of the lock range is 10 megahertz, I guess a better way of answering the question would be F can go between 10 megahertz plus kT over 2 pi down to 10 megahertz minus kT over 2 pi. And kT,
So would that be 10 megahertz, 10.01 megahertz to like 9.999
that's right.
or something?
Well, actually,
Okay.
yeah, because kT over 2 pi in this case is 10 kilohertz, right? It's 10 to the 4th hertz. So you're right, 0.01 megahertz, right?
Yeah. So not a lot of range.
No, pretty small. That's the nature of phase locked loops, though. The carrier frequency can be high and the tuning range is going to be small because it's just an allocated bandwidth. If you were demodulating a signal with this phase locked loop, you'd be able to demodulate an FM signal that would have a bandwidth, a message bandwidth of around 10 kilohertz or less, maybe only 5 or 8 kilohertz. And then the loop would be a little bit wider than what it needs to be. Okay, the second problem has to do with the final value theorem and the phase locked loop. So we studied this last time, and there's a nice discussion of that in the notes, but if you had to do this from scratch, you would have to take, you'd be going over here to use the final value theorem, limit as s goes to 0 of s times phi of s times 1 minus h of s, because that's the loop error function. And then you'd have to go put everything into the Laplace domain at this point. So you'd have, and I'll get you a cleaner version of this, limit as s goes to 0, and then you'd have 2 pi times 2e4 over s squared, right? Because we have a ramp here. We have a t over here, so we're ramping in phase. So it's just not a phase step, which would be a 1 over s. It's a phase ramp, so it's 1 over s squared. And then we have a pi over 3, and that would be pi over 3 over s, because that's a phase step. And then we have to bring in our 1 minus h of s. I'm going to throw that in here at the end, and 1 minus h of s, we can get that from up above. That would be 1 minus kt over s plus kt, and over a common denominator, that would be s over s plus kt. So this would be s over s plus kt. And then we could go cruising along with our final value theorem. We would be making some simplifications here. We would have, let's see, we can factor an s out of, let's see, how do I want to do this? We've got two terms inside of here, so we have to deal with both of them separately and taking the limit. But we're going to have an s squared right in here, and that s squared could be absorbed into the denominator to get rid of the s's we see in there, but then we'd end up only getting rid of 1 in here, so we'd still have an s sitting up there. So letting s go to 0 now is going to mean that the second term is going to be nothing, and the first term now is going to be 2 pi times 2e4 over S plus KT, and let's see, I'm missing, yeah, over S plus KT. Remember, the two S's got absorbed already, so we're going to have that. So that's going to be 2 pi times 2e4 over KT. So that is going to be your static or steady state phase error that you're going to get out of that. And we kind of worked through a problem like this last time, not in this exact context, but it was very similar to this. It's a first order loop, and it cannot track a frequency step, which is what this is. This is a 20 kilohertz frequency step. First order loop cannot track it without having some phase error in order to tune the VCO to follow the input, and that's what's going on right there. So we can quickly work through this problem. I know we're past time, but would you like me to work through this one or just give you the answers?
Yes.
Okay, I'm fine carrying on. So let's go down and do part B first, since it's the easiest part. It says, what value of M is required to make the frequency step size of the synthesizer be 10 kilohertz? So in this case, we're at 10 megahertz, so I have not started up my Jupyter like I had running before for my calculator, so I'm just going to do that real fast. Activate the right base. And by the way, if you can manage it, I can't stop you from using Python. It's not really an issue for me because you're just going to be using pencil and paper for stuff. I'm not.
Do you think I'm that fast at Jupyter coding?
Well, somebody's going to ask me that question, and Dr. Trimboli discussed that with his how his 2610 class worked, and he said they don't have time to do that stuff, but he made them agree to an honor code that they couldn't use it. As far as I'm concerned, using it as a calculator, though, is just fine, and I actually kind of like doing that myself. So I'm just launching the Qt console here, and then I'm going to get the font size bigger. I'm just using it, and I'm going to do PyLab on here, so I have all the functions loaded in automatically. So my system rebooted. There was a Microsoft patch that came on last night. So I'm just going to go down here and I'm going to say, okay, what would that be if I want to get this part B answered? I'd be looking at a step size to be 10 kilohertz. Well, remember when we're working with phase lock loop synthesizers, the frequency that goes into the phase detector from the reference oscillator is the step size. It's the smallest frequency step that the synthesizer takes. So if we want that to be 10 kilohertz, we can figure out that M 10 meg 10E6 over M has to equal 0.01 E6. So I guess we can do that one in our head if we want to. That would be 10 over 0.01, which would be 1,000, right? Make sure I'm doing that right.
So why does M say it equals 100 then?
Oh, in part A, it starts out as 100, and then it gets
Okay.
changed in part B. Remember, we're working backwards. So I would write down here that 10E6 over M must equal 0.01 E6, so that implies M equals 1,000. But in working part A, you're working with what's given, so my pen would cooperate there. Delete all that stuff. So in working part A, we want to find F out. So you would come into here, and the first thing I would do is I would say, what is my reference frequency? So it's going to be 10 megahertz divided by 100, which is going to put it over at 100 kilohertz, right? So that's 100 kilohertz. And the loop is going to lock when this frequency is 100 kilohertz. So we have to go through our math and say that, okay, our divider is set at 123. So if I go to the other side of the divider from 100 kilohertz, I'm going to be looking at 100 kilohertz times 123, and get the notation convenient on here. I'm going to go 0.1 K times 123, and that'd be 12.6 megahertz. Make sense? I'm just writing it in megahertz right from the get-go here. So so that tells us that F mix is, which is equal to F mix. So F mix is 12.3 megahertz, and I'm telling you that F mix is equal to F out minus F offset. So 12.3 is going to be equal to F out minus F offset, which is 100 megahertz. So that implies that F out is equal to 112.3 megahertz. Make sense? It's that easy. If you're wondering, it's that easy. It's not that overly difficult. The important thing is to not look at it and just sort of get blinded by, oh, I don't know what to do here. So the most important thing is to say that's your starting point. Those two frequencies have to be equal to each other. So you just kind of work backwards from there in this case. But I could take the same problem and turn it around, and I could say I want F out to be a certain frequency, and then I want you to tell me what N needs to be to make that happen. So you could work it that way too. I could take this exact problem and put this on the exam and just turn it inside out and just say the exact same setup, find N to get the output to be, a different frequency, like 121.2 megahertz. And another clue that you would have in working in that sense is this is the minimum step size, right? So you know that the output of the synthesizer is going to go in steps of 100 kilohertz. So we can produce values that are in that neighborhood. Now this eventually is going to be a limiting condition, but in a range of frequencies, and I will have it designed to work. So sound reasonable? And then of course what I did in the example last time was also say we're going to make this F out be a local oscillator frequency that might be tuning above or below to get an IF frequency at some other frequency. So I can combine this with another problem if I wanted to. I don't remember what I did in the old exams. I should probably wander over there and just take a look to see how creative did I get on these old exams in the synthesizer problem. This is a sampling theory, time division multiplexing. First order phase locked loop. Yeah, this exam doesn't have as many useful problems on it. It does have this page though. Okay, here's the synthesizer problem on this one. This is just a little bit twisted around in slightly different fashion, but it's still pretty similar to work out. These problems are pretty easy when you get right down to it. You just have to follow the block diagram, and you can see that in this problem, that idea of having those two be equal is right there. That's how we get that to go forward. I say I have a frequency doubler, so that means this is FL over 2. And then FL over 2 gets divided by 10, and then also gets divided by n. So that allows me to write this equation right here, just from that alone, set that equal to the reference frequency over 100, and then I can solve out for whatever I want to solve out for. In this case, local oscillator had to be high side tuning with a 10.7 megahertz IF, so you find out that's 110, and then you just plug everything in and pop out your n value. I want you to think of these problems as being the giveaway problems, because there's not a whole lot of, there's not any calculus involved. It's just simple algebra, just writing things down and using what you know to solve for what you don't know.
Will it be a static set of equations like the FREF, or like FREF divided by not like that. Oh, what is it? Because on the homework there was one where it used equations where it was like FREF equals n over or m over n f out or something.
Right. It'll
like, well,
it'll always be like this. It'll be something where you have enough knowns. It's kind of like your basic Ohm's law equations, right? E equals I times
Okay.
R, and then you're given two of the unknowns, and then you solve for the third. So there's always the permutation thing
Okay.
where you can spin it.
So if I write down a basic set of equations, there's not really a way to mess it up.
That's my feeling. But if you make a bad assumption because you're kind of like frozen, you know, your brain gets frozen sometimes, right? You get shell shocked, and then you kind of don't know what to do. You know, this is a Carson's rule problem in beta. We had that in a practice quiz. We had that maybe in a practice quiz, but these are nice problems. This is kind of a nice problem too. It's just involving the basic definitions of FM. There'll be a problem along these lines with time division multiplexing, and I don't know what I'll do for sampling theory. And then we have to traipse back further into chapter 3 because we didn't get through single sideband and mixing and super heterodyne and that stuff. So there'll be a question, there'll be a super heterodyne question, I'm sure, too. This old exam probably has a super heterodyne on it.
All right, I gotta go, Mr. Dr. Wigger.
Yeah,
You have a good day.
Fine. I don't know who else is left, but yeah, here's a super heterodyne. So there'll be one of those types of problems on there too. Who else is left since we're way over? Okay, we got a lot of people left. Does anybody want to ask some more questions?
So the practice exams that you posted are still good to go off of. That's usually what I use.
Yeah, exactly. So I can slide through these exams, and I can tell you right now which ones are not on the exam if you want me to just interpret like that.
Great. If you could ixnay some stuff to practice.
So on this exam, this problem is gone. That will be on the final. Yeah, so on this one, it's just that one problem that's gone. Page 5 is gone on the 2019 exam. And then on the 2018 exam, and I'm still running the video, so I'm capturing everything. Yeah. It will be, this is from Appendix A, so that will be gone, and this is from the end of Chapter 4, so both of those are gone. So again, it's page 5. This one started further down the line because the exam was probably later, exam 2 was probably later that semester, and last year was a hybrid, I think. Last year, I think the exam was given on Thursday of what would be next week, so I'd gotten one day further, but I didn't, you know, we voted, and I'm not at all, it's all within reason, but as far as I'm concerned. Things go really fast at the end. What I have to cover is not nearly is not that intense for me. I've got 3 lectures to do it, right? Because the exam is on Tuesday, then we'll have Thursday, and then Tuesday and Thursday of the following week to do that. I will get the project reworked so you can start looking that over, and we'll be able to talk about that a week from today. Get that up and rolling, and that will move quickly too. I'm confident of that. And the homeworks just sort of deteriorate into not much calculation at all, so they drop to a really low level of intensity. So we're past the high point. You have to get through this exam though, so you got to hold on. That's probably the main thing. Okay, who just asked a question from Colton? Oh, he just gave me his paper, so homework paper. So everybody else that hasn't given me their paper yet, you need to get that to me too. Yeah.
Professor,
Yeah.
This is John. I need to send you another homework
Okay,
10
that's
again.
fine.
Looks like I screwed up the one
Okay,
I
that's
sent
fine.
you. So I was just putting together the
Okay.
PDF wrong. So,
Sounds good.
all right.
Any other questions? We're down to 3 people. You haven't said anything today.
I'm out, Dr. Wickard. Have a good one.
Okay.
Thank you for your help.
Okay, we got 2 left. Jared, okay. Any more questions, or can I stop recording?